Hello, my name is Mark Lonsway, and today I will be walking you through and teaching math concepts surrounding question number 10 on page 87 of the Nelson Advanced Functions textbook. Before I indulge in the problem, I must first touch base with one of the concepts discussed in the problem, the basic properties of a cubic function. The basic cubic function can be resembled as the basic function shown on screen, modeled as f of x equals x cubed. The cubic function has transformations. These can be expressed through the formula f of x equals a bx minus h cubed plus k, where x is the inputted value, f of x is the output of the function, a is the vertical stretch or compression, b is the horizontal stretch or compression, h is the horizontal translation, and k is the vertical translation. Now to introduce the problem. To make a snow person, snow is being rolled into the shape of a sphere. The volume of a sphere is given in the function v of r equals 4 over 3 pi r cubed, where r is the radius in centimeters. Use two different methods to estimate the instantaneous rate of change in the volume of the snowball with respect to the radius when r equals 5 centimeters. The question here is related directly to the unit functions and their properties. Lesson 6 talking about instantaneous rate of change. To solve this problem, I have set out a list of steps. Step 1 is to highlight important details from the question. Step 2 is to get 2 points within 0.001 proximity of the point. Next, we will solve for the rate of change between these 2 points. We will then create the graph using Desmos and draw a tangent at r equals 5 centimeters. After that, we will calculate the slope of the tangent, then summarize our findings. From the question, we know that the cubic function that is given to us has a vertical stretch of 4 pi over 3 and no other transformations from the basic cubic function. Therefore, using Desmos, the graph will look as displayed on screen. The question also tells us that we are dealing with centimeters as our measurement for radius, which means that our units for volume will be centimeters cubed. The last thing the question tells us is that we have to find rate of change at r equals 5 centimeters, but before we can do that, we must first learn a bit about rate of change. Rate of change describes how one quantity changes in relation to another quantity. Typically, this will be how y changes in relation to x. However, for this question, rate of change will refer to how volume of the sphere, in centimeters cubed, changes in relation to radius of the sphere, in centimeters. The equation for finding the rate of change will be the common slope equation, y2 minus y1 over x2 minus x1. From what we have learned in terms of rate of change, there are two types, the average rate of change and the instantaneous rate of change. Average rate of change measures the rate of change between 2 points on a graph using a secant line that passes through both points. The average rate of change will be the slope of the secant line. Instantaneous rate of change, on the other hand, measures the rate of change at one specific point on the graph. Instantaneous rate of change is measured using the slope of a tangent line. A tangent line is a line that is parallel to and intersects the graph at one specific point. The question is asking for the rate of change of a snowball when the radius of the ball is exactly 5 centimeters. This leads us to calculate the instantaneous rate of change of the function at r equals 5 centimeters. One of two ways to do this is by solving for IROC algebraically. Since inputting only 5 centimeters for r will give us the volume at 5 centimeters and not the rate of change, we need two measurements of volume at two different radii. Therefore, we will add and subtract 0.001 to 5 centimeters to get values as close to 5 centimeters as possible. As a result, we now have two radii, which means we can get two different volumes at 4.999 centimeters and 5.001 centimeters. When getting your values for the volume of the sphere, make sure to keep all decimal places, for this could affect your values of IROC. Rather than using the common slope equation, y2 minus y1 over x2 minus x1 previously discussed, for this equation, we will be using the variable v rather than y, and r rather than x. So our equation ends up being v2 minus v1 over r2 minus r1. Using the values of volume and their related radii, we plug in the values into the equation and solve for IROC. By solving for IROC algebraically, we get the rate of change to be approximately 314 centimeters cubed per centimeter, but we are not done yet. Since the question is asking for you to solve for IROC two different ways, we must now solve for IROC graphically. As previously discussed, to solve for IROC, we must draw a tangent line at r equals 5 centimeters that intersects the function exclusively at r equals 5 centimeters. From here, we must find two distinct points on the line to find the slope of the tangent, or in other words, our IROC at r equals 5 centimeters. One point we know is on the line is the point at r equals 5 centimeters because we can use the original equation to get this value. Since we do not know the exact coordinates of our next point, to reduce our margin of error, we will use the x-axis to approximate our next point. With a point on the x-axis, we know for a fact that the y-coordinate of this point is 0, and for the x-axis, we will approximate the x-coordinate to be 3.33. By doing this, we are only approximating one of the x or y coordinates. From here, we now use the same equation from the last part to calculate the slope of the tangent. We plug in the coordinates 5, 523.5987756, and 3.330 into the equation v2 minus v1 over r2 minus r1, and get the slope of approximately 313.5 centimeters cubed per centimeter. Since the value is very close to our value when solving for IROC algebraically, we know we have done this process correctly. In the end, we get two slightly different values for our IROC at r equals 5 centimeters, but since solving for this problem algebraically is more accurate, we will use this value as our answer to the problem. So we sum up by saying, therefore, the rate of change of the snowball at exactly 5 centimeters is 314 centimeters cubed per centimeter, or in other words, the volume of the sphere is increasing at a rate of 314 centimeters cubed for every centimeter added to the radius, when the radius is 5 centimeters. In terms of the real-world application, the instantaneous rate of change of a sphere is used in solar geometry and the study of black holes. Near the end of a star's growth, after a red supergiant becomes large enough, it will undergo a process called a supernova, where the star explodes, then turns into either a black hole or a neutron star, depending on the size of the red supergiant. Current astronomers are trying to study black holes, but in order to find black holes, they must find large enough supernovas. Supernovas are very hard to come by, as they only occur 3 times every century. But black holes form when supernovas occur with a sun approximately 3 times the size of our sun. So astronomers must find a star that is both large enough to create a black hole and one that is on the verge of a supernova. Using instantaneous rate of change, the astronomers can find suns throughout the galaxy that are growing at a rapid rate, and they can estimate when the star will be the ideal size for a star becoming a black hole. Astronomers will also be able to see which stars are growing at a slower rate and thus which stars not to study if they want to find black holes. To sum up what was done today, we looked at a problem that dealt with the instantaneous rate of change of a cubic function at a certain radius. We then found both ways to solve for the IROC, algebraically and graphically, summed up our findings, then applied the concepts learned to the study of stars and black holes. That's all I have for you today. Thank you for listening.